the problems from maybe kinematics all the way to harmonic oscillator. So they help you to practice with the example problems. Okay. All right. See, do you see my screen?
Yeah.
Okay. So I have a bunch of problems. So I will read this problem and then I'll get you maybe like, I don't know, maybe 15 second, 30 second or 1 minute to think about it. And I'll just, you can maybe guess the answer and then I'll just, you know, um, show you the solutions and explain how to solve it. And then go one person at a time. I mean, one problem at a time. So number one, um, so let me read. An object is thrown horizontally to the right of a high cliff with an initial speed of 7.5 meter per second. Which arrow best represent direction of object velocity after 2 seconds? Assumed air resistance is negligible. Can you maybe guess which arrow indicating the best the direction of the object motion?
A.
A? After 2 seconds, not
Oh.
right after
mm,
the throwing an object.
C.
Yeah. Okay. So when objects thrown out of the cliff, obviously it comes with the horizontal velocity component as well as vertical component. In vertical direction, the object has free fall motion, and the horizontal direction, the object moves with the constant velocity. So after 2 seconds, horizontal direction, as I said, will have the free fall motion. If free fall motion described by this formula, the velocity in vertical direction is proportional to the initial velocity plus the acceleration times t. Acceleration now there is no initial velocity v naught, so the v naught is 0, and the vertical direction the acceleration is same as acceleration constant t, I mean g, and the time t. So after 2 seconds, that will be 10 meter per second times 10 meter per second squared times the 2 seconds. So that should be 20 meter per second. And the original direction, there's no acceleration component. So it should be same as initial velocity, which is 7.5 meter per second. So your resultant vector out of these two velocity component should be like this: vertical direction downwards with 20 meter per second, and the horizontal direction is 7.5 meter per second. So resulting vector should be combination of these two vectors should be like this, right? So that should be same as number C. Okay,
Mhm.
next one. So you see the graph of the velocity versus time. Number two, rank change in momentum for each segment from least most negative to the greatest most positive. Assume that the mass of the object remains constant. And uh, problem three is also about this graph. So during which segment is the magnitude of average acceleration greatest? Maybe you can just spend some time to think about it.
For 2, I got D, and for 3, I got C.
D, and 3 is C.
Mhm.
Okay, so number 2, um, the change in momentum is proportional to the change of velocity, right? Because there's no change of mass, so uh, the momentum must be a function of variation in the velocity in a given time. So the AB, the velocity variation along the AB is the 7 meter per second, right?
Mhm.
Here to 3. And then BC is the 0 meter per second, and the velocity CD is minus 4 meter per second. Number DE is, as you see that the DE is like reduced to the 0 from 3, so that should be minus 3 meter per second. And the variation of velocity EF is minus 2 meter per second. So if you rank the variation of velocity in the time segment, is now CD is biggest, and the DE next, and the EF, is it right? EF, and then BC is next one, and then it's just AB is biggest change of the velocity. And during which segment in the magnitude of average acceleration greatest. So this is about the acceleration. So we have to divide this the velocity by their time, right? So if you divide the velocity variation in the segment AB, then 7 divided by 3 is 2.3 meter per second. And BC is the acceleration is 0 divided by how much is 3 second. The 2 second, right? So that is 0 meter per second square. And the acceleration in CD is minus 4 meter per second divided 1 second. That variation velocity varies in 1 second, so the minus 4 meter per second square. And A along the DE is minus 3 meter per second over 3 seconds. So that is minus 1 meter per second square. And acceleration along the EF is minus 2 meter per second over 2 seconds. So that is minus 1 meter per second square. So from that, the greatest acceleration is in the CD. So that is number C. Okay, there's should be one more problem. And number 4, what is total distance traveled by the object? Can you guess?
Um,
Let me go back.
yeah.
Okay. So yes, this one should be something wrong. This should be actually like this. Okay.
Um, Does it ask for total distance or final distance?
You go back, let's check. Total distance traveled by object. So from A to F.
I got D.
How much?
D. 38 meters.
38? Okay, let's find out. So let me split. So the distance is the area of the velocity graph underneath the velocity graph, right? So the distance along the AB, the path AB is, so distance SAB is triangle 1/2 times 7 times 3. That's so velocity varies over 3 seconds, so that is 21/2 meter. And the distance BC 1/2. Oh, I'm sorry, not 1/2. That's the area of a rectangular area from B to C. So that is 7 times 2. It moves with the 7 meter per second over 2 seconds, so that is 14 meter. And distance from C to D, this area, right? That is 1/2 times, so that the velocity reduced from the 7 meter per second to the 3 meter per second. So that is 4/1 second. That velocity changed to 3 meter per second from 7 within 1 second. And there's also a rectangular shape right there. So that is 3/1. So that is 5 meter. And the area travel distance from D to E is 1/2 times 3 meter per second. The variation of velocity is 3 meter per second over how much? 3 seconds, right? So that is 9/2 meter. The last one, the travel distance E to F. Now it changed from 0 to the -2, so that is 2. So that 1/2 times 2, that happened over 2 seconds times 2, so that is 2 meter. You have to just add them all, right? So that total distance, travel distance is SAB, SBC, SCD plus SDE plus SEF. Now that is what? So you plug 21/2 plus 9/2. This one is same as 15 meter if you add them together. 15 meter, 5 meter is 20 meter, and 42 plus 2 meters. The total is 36 meter. Okay.
Mhm.
So if this question asks you about total displacement, then how much will be the total displacement then? It's asking total distance, right? But if the question just changed to total displacement, then how much would be?
Um,
So now you know the difference between distance and displacement.
-13 meters.
No. Take a look at the graph. The graph tells you the how much number that travel this displacement would be. So basically, let me just explain the difference between the distance and displacement. Distance is magnitude of the displacement. So displacement is vector and the distance is scalar. So now if you look at this graph, objects just moves along the one dimensional space with this amount of travel distance, and when you reach to the end of the point E, from A to E, it starts to move back actually because it's negative sign, -2. So it has -2 meter back. So that should be F. So it will be like this. This is A, this is E, this is F, right?
Mhm.
So this question asks you, scalar quantity, which is the total travel distance. Then you have to add a magnitude of the displacement from A to E and E to F. So this is 30, how much? 34 meter.
Mhm.
And we have E to F is -2 meter. But that's also minus sign indicating the direction of the movement. So if the question asks you about total distance, then you have just add the magnitude of displacement. So 32 plus 2 meter, which is 36 meter. But if it asks you about the displacement, total displacement, then only thing you have concern is the starting point and end point. So starting point A to end point F. You gotta just now this object moving to the moving to the E and then return back to the A with the -2 meter. So you have to subtract the 2 meter out of the 34 meter. So 34 -2, which is 32 meter. That is displacement, total displacement. You see the difference between the
Yeah.
distance and the displacement? So one more time, displacement is vector and distance is scalar. The magnitude of the displacement is distance. Okay?
Mhm.
All right. Let's move on. Number 5. Ball is thrown with the initial velocity v at an angle theta above the ground. If the acceleration due to the gravity is -g, which of the following is the correct expression of time it takes for the ball to reach its highest point, y, from the ground? All right, think about it and let me know.
C.
Okay, yes. So this one, vertical direction, in vertical direction, velocity vector Vy is as I already told you, initial velocity plus acceleration times t. So here, initial velocity Vy, in the final velocity, when this objects reach the maximum height, velocity component Vy must be equal to 0, right? Because that is a stop and maximum height spot, maximum height, and the start to drop down. So the final velocity at the maximum height should be equal to 0. So if you put that 0, and the AY acceleration component is gravitational acceleration constant minus G, is the pointing downward. So you plug that, then T must be minus V initial velocity divided by gravitational constant minus G. So that is BOY over Z. And now BOY is what? The initial velocity V naught times sine theta. So you just plug that into this equation. Then the time T is V sine theta over Z. Very straightforward. So that is C. Okay. Next. The bubble in the glass of water, as you can see in the picture, releases from the rest at the bottom of the glass and rises at acceleration a to the surface in t second. How much farther does the bubble travel in its last second than in its first second? Assume that the journey takes longer than 2 seconds. Can you guess?
Um, E,
E, you mean E?
B.
B?
Mhm.
Okay. So let's take a look. So for first 1 second, travel distance d1 is initial velocity v naught times delta t plus 1 over 2 a times delta t square, right? So there's no initial velocity, so that's 0 times 1 second. Oops, there's one. Hold on. Okay. Oh, oops. Once times 1 second plus 1 over 2 a, then 1 second square. So that is 1 over 2 1 second a, right? We don't know the acceleration, but doesn't matter. We're gonna use that as part of the variable. For final second t final second, distance, travel distance dt is a, and t minus 1 second, 1 second, plus 1/2 a 1 second squared. So that is a t minus 1 times 1 second plus 1/2 1 second squared times a. So your the bubble travel in the last second, then it's first second, then that is dt minus d1. So that is obviously if you take this one out of the dt, then that is a t minus 1 second. I mean meter. Okay.
Mhm.
All right. So that is B. Okay. Now hopefully you can actually see this screen. So the person standing on the horizontal floor is acted upon by two forces: the downward pull of gravity and the upward normal force of floor. These two forces A have equal magnitude and form an action and reaction pair. B have equal magnitude and do not form an action and reaction pair. C have unequal magnitude and form action and reaction pair. Number D have unequal magnitude and do not form an action and reaction pair. Which one do you think is answer?
Mm. B.
B. Yeah. So the weight normally it balanced with the normal force in magnitude, but it's not from an action reaction pair, right? So in order to form the action reaction pair, two forces must come from the two objects acting on each other. So one action reaction pair is in this circumstance is the person and Earth from gravitation, and the other action reaction pair in this case is person and the floor with the normal force. Okay, so number B is correct, that the two forces have equal magnitude but do not form action reaction pair. Okay. And number 8, which of the following graph best represent the force of friction on an object starting at a rest that eventually starts sliding across the level surface due to the gradually increasing horizontal force?
B.
B. Uh, just before objects on the surface with the on the rough surface moves, it experiences the static friction, which is proportional to external force. So the more force applied to the object, objects have more higher and higher increasing force. But once the object starts moving, then so the frictional force which was used to stop the object is suddenly just dropped down at the point the object start to move.
Mm.
And then the object, once it starts to slide, then experienced actually constant friction. So that is nature of frictional force. So there are two different regimes, the static friction and the kinetic friction. And before object moves, the frictional force, linearly increase to the maximum point. But once, as I said, once objects start to move, the atomic force between the two different surfaces is completely changed, conditionally changed, and then that make less resistance on the surface. And while it moves slide or moves over the rough surface, it experiences constant frictional force. With that idea, what do you think? Which one do you think it is answer?
D.
D. As I said, that's the frictional force linearly increase in terms of external force. It's got to be the increase up to some point, the maximum frictional force in terms with respect to the external force.
C.
Yes, C. So as I said, that's frictional force should be increasing the proportional to the external force up to some point. But once the object starts to move, then suddenly the frictional force, the barrier is drops down, and then objects start to move with a constant frictional force or resistance on the surface. Okay.
Mhm.
Okay, number 9. Two objects have a mass of 1 kilogram and they carry a charge of a magnitude 1 coulomb each. Which statement correctly identifies the relationship between the magnitude of force of gravity, Fg, and the magnitude of electric force, Fe, between the object. So, for FII, electric force out of charge is normally defined by this formula, K Q naught Q2 times R squared. Here K is Coulomb constant, that is 9 times 10 to the 9. And as you know, the gravitational force is in the same form. Z, as you remember, times 2 mass M1, M2 over R squared. Here is G is 6.7 times 10 to the minus 11. So with that idea, this is case of the two charges, they separate with distance R. This gravitational force, similar configuration, two masses, distance separate with the distance R2. Okay, so this question asking which force is bigger. So basically, this universal gravitational constant number is way, 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 way smaller than this electric force constant, Coulomb force constant term is by 10 to the 18. So Fe is way bigger than gravitational force in general. Okay, so the answer should be B. Okay.
Mhm.
And the next one, consider the above configuration of masses attached via the massless above and the pulley over frictionless inclined plane. What is the acceleration of masses? The easiest way is just try to select solution answer by process of elimination. Do you know what the definition of the process of elimination?
Like cancel out the variables.
So like this is a multi-choice problem. If you find that one condition that apply to the all 4 choices and then get rid of obvious and the and not the choices which not correct, and take that, exclude that out of your choices, and just get rid of them from your list. That
Mhm.
is sometimes called the process of elimination. So that is probably the easier way or faster way to solve this problem. So then you have the figure right there, right?
Mhm.
So, so let me
I think it's B.
B.
Yeah.
How did you solve it?
Um, because I didn't think that G and A were correct. And when like solving these problems, I always use like sine theta instead of cosine theta.
Okay, yeah, that's good approach. Because in order to these two masses stay in balance, and forces applied to the downward on the M2 should be same as the force applied along the slope of this inclination, right? So this force should be same as F2, same as F1, right? So, but here F1 is mg times sine theta. So sine theta must be into description of this relationship. So if you take a look at the A, B, C, D, only B has sine function in the description, right? So the B must be answered. That is the easy, fastest way to find the answers out of these choices. Okay. I mean, you can have like explicitly just solve the whole problem more systematically, just but the multiple choices, you don't have to waste your time. Just once select the answer, then move on to the next one. Okay. So number 11, the person is pulling block of the mass m with the force equal to its weight directed 30 degrees above the horizontal plane across the rough surface, generating the friction F1 on the block. If the person is now pushing downwards on the block with the same force 30 degrees below the horizontal plane across the same rough surface, what is the friction on the block? Um, uh, Mu K is the coefficient of kinetic friction across the surface.
2 or C.
C,
Yeah.
that's your answer?
Yeah.
Okay, so let's take a look. So frictional force F is frictional coefficient times normal force N. So now you have block and the person pulling the block with 30-degree above the horizontal direction on the surface. So there should be two forces. One is this force split into the vertical component and horizontal component. So the vertical component is mg sine the theta, which is 30-degree. So that is against that the gravitational force out of this block, which is mg. So normal force itself is mg gravitational force, which is generated by this block itself, minus the vertical component of external force, which is mg sine 30-degree, right? So you gotta actually multiply this to the frictional static frictional coefficient. So the frictional force is mu k mg minus mg sine 30-degree. Here 30 is 1/2, so that should be 0.5 mu k mg, right?
Mm.
So now if you pull down that block, but the downwards, like with 30-degree, right? Then asking how much frictional force that the block will experience with that 30-degree down. So from that, you have also still have vertical component, but it's downward. So that normal force should be the mass, the weight of this block itself, plus you have the external force, particle component of external force, but in the same direction with the uh, gravitational force, the weight. So that should be mg sine 30-degree. So that is 1.5 mg. Right. So the frictional force and second, I mean the external force apply in 30-degree downward, and that is mu k times 1.5 mg. So here mu k from the first condition, mu k is F divided by 0.5 mg. You plug mu k into this formula, and that is F over 0.5 mg times 1.5 mg. So if you can cancel mg out of numerator and denominator, and so then that should be 1.5 over 0.5 f, that is 3f. So the answer is actually D. Okay.
Mm-hmm.
All right. Let's move on. Number 12. In the figure above, the two blocks of a mass 3m and the 2m are attached together. The plane is frictionless and the pulley is frictionless and the massless. The inclined portion of the plane create angle theta with the horizontal floor. What is the acceleration of the block 2m if both blocks are released from the rest?
I got B.
B, okay. All right, so in this isolated system, the driving for net force, only net force applied to this system move is the gravitational force along this surface of block 2M. So that is F net, the net force is 2M times G sine theta. And with that, the force, total system moves together because the 3M and 2M, they attach to each other. So that should be total mass M times acceleration A. So that is system acceleration A. So total mass is 3M plus 2M, which is 5M. So why is that? The A must be 2mg sine theta divided by 5m. The m is canceled out, so that is 205 g sine theta. So that is answer is B. And number 13, if a roller coaster cart of mass m was not attached to the track, it would still remain in contact with the track throughout a roof of radius r as long as what?
I got B.
B. Okay. So when this roller coaster cart reached the top of this roof, if gravitational force bigger than greater than centrifugal force, then this cart will just drops down, right? So the condition for the cart to stay in the loop is must that centrifugal force must be larger than gravitational force. So from that condition, centrifugal force is mass times velocity v squared over radius r of the loop. It should be larger than gravitational force mg. From that, velocity it should be larger than square root rg. Okay, that's straightforward. And now number 14, the diagram above shows the top view of an object of mass m, large M, on a circular platform of the mass 2, large M, that is rotating counterclockwise. Assume the platform rotate without the friction. Which of the following best describes the action by the object that will increase angular speed of the entire system? A, the object moves toward the center of the platform, increasing the total angular momentum of the system. B, the object moves toward the center of the platform, decreasing the rotational inertia of the system. Number C, the object moves away from the center of the platform, increasing the total angular momentum of the system. D, the object moves away from the center of the platform, decreasing the rotational inertia of the system.
Um, I think it's B.
Okay. So basically, the rotational platform and the object resting on the platform consist of an isolated system. So in the isolated system, angular momentum must be conserved, so it should remain constant. So in that case, you can get rid of A, you can exclude A and C, right?
Mhm.
And to decrease rotational inertia, um, then the objects you have to move that object toward the center of the platform because the definition of rotational inertia is what? I is the mass times r omega squared. So if you stay close to the center of the rotational axis, then you have a lower, smaller rotational inertia. So in that sense, that B is should be the answer. Okay. And number 15, a moon has elliptical orbit about the planet as shown above. The moon's mass is much smaller than the planet's. Each of the following the quantities are approximately conserved as the moon moves from the point A to point B. Uh, one, the moon's mechanical energy. Two, moon's angular momentum. Three, the moon's linear momentum.
I think A.
Okay, that's correct. So if the moon and planets are treated as a single system, the system's total mechanical energy and linear momentum and angular momentum are all conserved. But that's not necessarily the true for each object individually the moving. So the moon is now moving. See that moving toward the top of the page now there. It's like this, right? Right? At point A, but toward, but that's the toward also the B, and that's the velocity they change along the A to B and B to A. So that change the velocity of the moons change a lot. So its momentum changed as well because mass doesn't change. So the velocity change, the momentum, linear momentum must be changed. So uh, the moon's linear momentum is not conserved in this system. So any choices, including the three, must be excluded out of these choices, right? So B, C, D shouldn't be answer. Only A, which include 1 and 2, must be answer. Okay. All right. Number 16. The spear start from the rest atop a hill with the constant angle of inclination and is allowed to roll without the slipping down the hill. What force provide the torque that causes the spear to rotate? A. Static friction. B. Kinetic friction. C. The normal force of the heel on the spear. D. Gravity.
Is it B?
You're close, very close, but kinetic friction is more like friction applied to the moving object. But remember that when torque is created,
Mhm.
that force applied to the rotating system must be perpendicular to the radial vector. So when this, if the spear is rolling along this inclination, only one point should touch that surface of inclination. In that sense, the some friction must be strong enough to hold the spear from the slipping and sliding. I'm sorry, the sliding. So frictional force is more like moving object over the surface. So that object must be moved with the friction itself. So let me just draw the picture. You have inclination and you have spear, and obviously torque is should be the um, this is the radial like component, and the torque was the R cross product F, right?
Mhm.
So the F component should be this configuration of the spear must be perpendicular to the radial component on this the point of action. So now the gravity is normally applied to the center of mass and now it's downward. So it's not the case. And normal force same is perpendicular to the surface, the same direction with the radial vector R. So the normal vector is also is not answer. And there's only two choices, static friction and kinetic friction. So the kinetic friction is created, kinetic friction occur when this object move over the surface.
Mm.
Okay, so that is not applicable to this rolling objects because in that case, this sphere must be moved with only translational component, UK. So in order to have rolling motion, this surface of this inclination must hold this point of the spear, which create the force perpendicular to this R vector. So only static friction is applicable to this circumstance, which create the torque over the sphere.
Mhm.
Okay, so that is number A. Okay, that's it for today. As I said, we will continue this AP test preparation. We're gonna solve the example problems every week.
Mhm.
If you have a question along this session, and also if you have follow-up question, just email me anytime. I'll just
Okay.
get back to you. Okay.
Mhm.
To make sure you just email me the Zoom video file.
Mhm.
All right. I'll see
Yeah.
you Sunday. All right. Bye.
Okay. Bye.
Mhm.